All right. So in this video, we will solve the second order differential equation to y double prime plus 3xy equal to 0 using a power series centered at x equals to 0. All right, so we will assume a solution of the form y equals to sigma n equals 0 to infinity of c sub n x to the n. In this case, unlike previous examples, we will go all the way to the second derivative because see how the differential equation, which is a second order one, requires to find the second derivative of the power series. That is y double prime equals to sigma n equals to infinity of n times n minus 1 c sub n x to the n minus 2. Essentially, we're using the general power rule to differentiate the x to the n minus 1. All right, so we may go ahead and simply substitute the derivatives. In this case, be careful. Notice in this case, the first derivative does not appear in the differential equation. So we just use the original function and its second derivative. That is 2 times sigma n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2 plus 3x sigma n equals 0 to infinity of c sub n x to the n, and let that be equal to 0. All right, so there's not much to do as far as you'll see, as far as combining series and all that. Well, number one, that's to let the 2 be introduced into the series as well as the 3x into the second series. So sigma n equals 2 to infinity of 2 times n minus 1 c sub n x to the n minus 2 plus sigma n equals 0 to infinity of n 3x, or rather 3 times c sub n x to the n plus 1. In this case, the n plus 1 comes from multiplying x times x to the n at the powers x to the n plus 1. And let that one be equal to 0. All right, well, so in this case, we would need to combine the series together so we can come up with a recurrence relation to generate the coefficients and write our solution in sigma notation if possible. Spoiler alert, it will be possible for this one. All right, okay, so in order to combine the two series together, we need to have the two series with the same starting index and the same power of x. So we might want to write all series, in this case the two series, in terms of x to the n plus 1. However, the first series, which has a power n minus 2, it would actually take 3 units to go between -2 to +1. Okay, well, if you're thinking of doing a complete shifting on the first series, that is adding 3 to all of the n's right here, that would imply subtracting 3 units to the starting index. However, that's going to take us 1 unit into the dark side of the power series, and you don't want to go there. Well, how do we prevent that going into the dark side? Well, expand n equals to 2, the term for n equals to 2. And for this, well, we go back to, so this would be, okay, for n equal to 2, that is 2 times 2 times 2 minus 1, which is 1, right, times c sub 2, x to the 2 minus 2, plus, now that we stripped off the term related to n equals to 2, the series now should start at n equals to 3 to infinity, 2 times n minus 1, c sub n, x to the n minus 2, plus sigma n equals 0 to infinity of 3 c sub n, x to the n plus 1, and let that be equal to 0, right? Okay, so at this point, we may go ahead and perform the complete shifting to the first power series. That is, I'm gonna subtract 3 to the starting index. That is, I'm gonna add 3 to all ends into the series. All right. That's not only going to turn that n equals to 3 into an n equals to 0 to match the starting index with the second series, but also it will match the power of x to go from n equals to n minus 2 to n plus 1. All right. So let's let me clean up the first term we expanded. That is 2 times 2 times 1, which is 4 c sub 2, x to the 2 minus 2, that's x to the 0, which is 1 times 4 c sub 2, that's simply 4 c sub 2. N equals sigma n equals 0 to infinity of, be careful, that is 2 times n plus 3 times n minus 1 plus 3, is that an n plus 2, c sub n plus 3, x to the n plus 1, plus sigma n equals 0 to infinity of 3 c sub n x to the n plus 1. Let that be equal to 0. All right, now that we have the two series with the same starting index and the same power of x, we may go ahead and combine them together. So that's going to leave us with 4 times c sub 2 plus sigma n equals 0 to infinity of bracket 2 n plus 3 n plus 2 c sub n plus 3 plus 3 c sub n. That times x to the n plus 1. And let that be equal to 0. All right? Okay, so at this point, we may go ahead and equate coefficients. So the constant term on the left must be equal to the constant term on the right-hand side. In other words, simply for c sub 2 equals to 0, that means c sub 2 equals to 0. And on the other hand, the coefficient of x to the n plus 1 on the left, which is all this madness over here, should be equal to the coefficient of x to the n plus 1 on the right-hand side. But there's nothing on the right-hand side. That means the coefficient equals to 0. So again, 2 times n plus 3 times n plus 2, c sub n plus 3 c sub n equals to 0. So solving this equation for the c with the largest subscript in this case, for c sub n plus 3, it's going to give us the recurrence relation. So let me go ahead and do that. So I'm going to subtract 3c sub n on both sides, and then I'm going to divide both sides by the quantity 2n plus 3 times n plus 2. All right, here we go. So that's going to leave us with the following: c sub n plus 3, okay, that equals negative 3 c sub n divided by 2 times n plus 3 n plus 2. Okay. All right. So now again, everything we have here is providing us with a lot of very important information. Well, number one, uh, it seems like each coefficient that we're going to obtain will depend on three indices earlier. That's because the difference between n plus 3 and n is 3 units. All right. So that means the coefficients will split into this time three independent chains. That is, one change for c sub 0, another change for c sub 1, and then another change for c sub 2. Right. So we're going to add, I'm going to add 3 to all of the subscript in the first chain. So that'll be C sub 3, C sub 6, C sub 12, etc. And then at C for C sub 1, add 3, that's C sub 4, C sub 7, C sub 13, and go on. And for C sub 2, that the next one will be C sub 5. At 3 to 2, that's C sub 5, C sub 8, and C sub. So 8 plus 3, that's 11. Wait, 8 is 5, 8, C 11. All right. Okay. So now what's important about this? Well, the term we stripped off when we were fixing the series in the previous steps, that tells us that C sub 0, C sub 2 equals to 0. So that means C sub 2 equal to 0, and all of its subsequent terms in that change of coefficients are also equal to 0. So in this case, we will only need to compute these two chains of coefficients. That is, the chain corresponding to C sub 3n and the chain corresponding to C sub 3n plus 1. All right. Okay, so let's see what we do. So actually, I'm going to compute the coefficients for the first chain of coefficients in one side work, and then the second chain of coefficients in another side work. So let's do the C sub 0, C sub 3, C sub 6, C sub 12. All right, so that is, in other words, for C sub 3n, in other words, that is C sub 0, C sub 3, C sub 6, etc. Okay, let's compute for n equals to 0. So for n equals to 0, where's our recurrence relation? Keep in mind our recurrence relation. Can we box it? So that'll be C sub 0 plus 3, which is 3, equals to negative 3 times C sub 0, everything divided by 2 times 0 plus 3, which is 3, times 0 plus 2, which is 2, right? Well, that's all it is for this factor. Do not cancel out the 3's, do not multiply anything, just leave it like that. By the way, worth noting, this is going to be the coefficient of x cubed. You'll see. All right. And then for n equals to, what is that? For 3, okay? For 3. That is c sub 3 plus 3, which is 6, and that equals negative 3 c sub 3 divided by 2 times 3 plus 3, which is 6, times 3 plus 2, which is 5. And well, in this case, you might want to write c sub 3 in terms of c sub 0. So this will be negative, as we have done it before in other exercises, 3 divided by 2 times 6 times 5 times c sub 3, which is 3 c sub 0 over 2 times 3 times 2. All right? Okay. Uh, how do we simplify? Well, not simplify, combine some of the powers. Okay. I know there's three twos right here. Just let alone these last two. So I'm gonna write this 3 times 3 as actually, well, this would be a negative. Now this becomes a positive. So that's it. That is 3 squared divided by 2 times 2. That's a 2 squared. And what are we going to have here? 6 times 5, 3 times 2. Okay? 6 times 5, 3 times 2. And that's a c sub 0. Right? And then so that's for n equals to 3. The next n for n equals to 6. Okay? Let me actually drag the recurrence relation because I don't want to scroll up and down every single time. Right? So I'm going to use it for reference. Okay. So recurrence relation is here. So now for n equals to 6, so that is c, so 6 plus 3, that's 9, equals to negative 3c sub 6 divided by 2 times 6 plus 3, which is 9, times 6 plus 2 is that equals to 8. Okay. However, you might want to write c sub 6 in terms of c sub 0. That is, okay, number 1, negative 3 over 2 times 9 times 8, open parentheses, and write the previous term for c sub 6, which is 3 squared times c sub 0 divided by 2 squared times 6 times 5 times 3 times 2. All right? Okay, so this reduces to, what is that? This reduces to negative, okay, make this a little small. All right, so this is negative 3 cubed divided by 2 cubed, and then the product, 9 times 8, 6 times 5, and 3 times 2. All right, and that times c sub 0. So we are essentially done with the coefficients with subscript 3 times n. That is c sub 0, c sub 3, c sub 6, c sub 9. All right, so that is the first chain. Let's have a look at the coefficients for the second chain. That is C1, C4, C7, C13, etc. All right, so let me add another page for this. And let me also bring the recurrence relation with us. All right, so we're going to need it. That's fine. Copy and paste. And let me box it. We really need it. All right. So 4, okay, so this time around, let me write this 4. The coefficient of the form C sub 3k plus 1, okay, that is C1, C4, C7, etc., right? So that's going to be, okay, n equals to 1. I'm going to start at n equals to 1 this time. That's going to give us, okay, c sub 1 plus 3, which is c sub 4, equals to negative 3 c sub 1 divided by 2 times 1 plus 3, which is 4, times, wait, come on, what happened here? Okay, 3 c sub 1 divided by 2 times 4 times 1 plus 2 times 3, right? For n equals to subscript 4, that equals c sub, okay, 4 plus 3 is that equal to c sub 7, and that equals to, okay, negative 3 c sub 4 divided by 2 times 4 plus 3 is that equal to 7 times 4 plus 2 is that equal to 6. And well, you might want to write this coefficient not in terms of c sub 4, but in terms of c sub 1. See how we wrote all of these coefficients here in terms of c sub 0. Now the second set of coefficients will be written in terms of c sub 1. That's actually our C1 and C2 arbitrary constants when we solve this kind of equations, but not using series. You'll see how is that going to work. Okay, so number one, that's equal to 3 divided by 2 times 7 times 6, and that times negative 3 c sub 1 over 2 times 4 times 3, all right, which reduces to negative times a negative. This is positive 3 squared divided by 2 times 2, that's 2 squared, times 7 times 6 times 4 times 3. And this is in terms of c sub 1. All right. Okay, let's compute one more so we can see a pattern. Actually, well, yeah, let's do it. N equals to, what was the next one? 7. N equals to 7. That equals to c sub 7 plus 3 is that 11? No, I mean 10. That's 10 equals to, yeah, 3 c sub 7 divided by 2 times, okay, 7 plus 3, which is 10, times 7 plus 2, which is 9, which is negative 3 over 2 times 10 times 9 times all of these humongous coefficient in terms, not in terms of c sub 7, but in terms of c sub 1. This will be 3 squared divided by 2 squared, 2 squared times 7 times 6 times 4 times 3, right, in terms of c sub 1. And simplifying all of this, okay, make some room first. This will be equal to negative 3 cubed C1, okay, and then divide everything by 2 cubed. These two with these 2 squared becomes a 2 cubed. And then we're going to have the somewhat descending product 10 times 9 times 7 times 6 times 4 times 3, right? Okay, so let's see, times 6, 4 times 3. All right, so we're essentially done computing the coefficients of the series. Now, again, see how this set of coefficients we obtained over here are all in terms of c sub 1. All of these coefficients we computed before are all in terms of c sub 2. That's because all of these coefficients are going to be of some of the terms of the power series um, in terms of c sub 0, which are going to be part of the first linearly independent solution to the differential equation. And likewise, all of these are going to be part of the terms containing a c sub 1 corresponding to the second linearly independent solution. That's because we are working on a second order differential equation which has two linearly independent solutions. All right. So now let's write those in polynomial form. Okay, so writing this in polynomial form, and we are almost done with the solution to the differential equation. Okay, so let me write. Okay, this is what I'm going to do. I'm going to write. Notice how all of these terms have a c sub are in terms of c sub 0, so I'm going to start with c sub 0. Okay, I'm going to factor c sub 0, so c sub 0 times, okay, the first coefficient that's simply a 1, and then minus what's the second coefficient, that is the corresponding to one corresponding to c sub 3, that is negative 3 over 2 times 3 times 2. Okay, so let me just copy it down. 3 over 2 times 3 times 2, and that's actually the coefficient of x cubed. How do we know that? Because it's c sub 3. And again, the subscript that we see here correspond to the power of x in the term of the series, right? C sub 6, it's all this madness here, and C sub 9, all this madness over there, right? Let me write them down. So the next one is positive 3 squared divided by, let me actually do it here, 3 squared. Um, that'll be 3 squared over 2 squared times 6 times 5 times 3 times 2, and that's the coefficient of x to the 6. Okay, and then another minus, and then this will be a 3 cubed divided by 2 cubed times 9 times 8 times 6 times 5 times 3 times 2. All right. Okay, so this is what we're going to do here. So, oh, that's also the coefficient of x to the 9. All right. And then, of course, plus infinitely many terms. All right. Mhm. Mhm. So that's the first fundamental solution, the first linearly independent solution plus c sub 1 times, okay, here the for n equals to 1, that's essentially this. We start with the c sub 1. But in this case, c sub 1 is the coefficient of x to the first power, and then minus the coefficient of x to the fourth, and then the coefficient of x to the 7, and then the coefficient of x to the 10. All right, and here we have the coefficients. Negative 3 over 2 times 2 times 4 times 3, right? And then that's x to the fourth, and then plus 3 squared divided by 2 squared, okay? 6, no, 2 square times 7 times 6 times 4 times 3. Essentially, all of these numbers you see here are shifted by 1 unit with respect to the first fundamental solution. And that's going to be that recognizing that pattern will help us a lot to get the series solution. That's x to the 7th power, and then minus what's next? 3. Okay, so 3 cubed divided by, what is that? 2 cubed times 10 times 9 times 7 times 6 times 4 times 3. This is the coefficient of x to the 10, and then plus infinitely many terms. Okay, so at this point we should be able to write the solution in sigma notation for the two series, actually for the two polynomials. Well, so looking at the numerical pattern here, well, one thing that stands out to me is, well, did you see this 9 right here and all of the numbers multiplying? Uh, that looks like the factorial, but it's not quite the factorial because we're missing some of the factors. That's also coinciding with, what is that? With the power of x. Okay, so we could actually write this in factorial form if we had those missing factors. That is, um, I wish I had the 7 right here and the 4 over there. Well, we don't need to write the 1 because it's an invisible one. Well, actually, we can make our wish come true because check this out. If we if I multiply by a 7 here, okay, and I multiply by a 4 over here, then I need to multiply, and I multiply by an invisible one. I'm gonna add that one over there. So I can do a 1 times 4 times 7. Same over here. I'm missing the 4 and the 1. 1 times 4. Over here, I'm missing the 1. Multiply the 1. In the second series, well, what do we have? Do you see the pattern? 10, 9, we're missing the 8, 7, 6, we're missing the 5, 4, 3, we're missing the 2, and naturally the 1. We need to write that 1 over there. However, what I'm trying to say here is that product of numbers, of integers, coincides with the power of x. Well, so let me actually then do the multiplication by multiply by 8, multiply by 5, multiply by 2. Then do that in the numerator as well. 2 times 5 times 8. All right. Okay. So in this case, okay, so for the previous term, 7 times 6 times 5 times 3 times 2. So I need a 2 times 3. And then we're missing a 2 here, multiply by 2 in the numerator. So here we're going to see these increasing products that we have been looking at in previous examples. All right. And again, for this kind of series, you might want to look at write them in sigma notation only for the ones from the second term of each and on. Exclude the one for the first polynomial and exclude the x for the second polynomial, because otherwise that'll make us start the series at n equals to 0, and we're going to have trouble, as we saw before, with those series. Okay, so let's finally write the solution as a power series. Well, number one, so our solution, that is y equals to c sub 0, that is 1 plus sigma n equals 1 to infinity of, what do we have? Alternating series, all right? Negative 1 to the n. So we need an alternating factor here. And then, well, from the pattern, do you see how do we have n equals 1, n equals 2, n equals 3? All right, so let me actually be a bit more explicit with that using different colors. So n equals 1, n equals 2, n equals 3. Same over here. N equals 1, n equals 2, n equals 3 for the second series. I mean, okay. So what I see is 3 to the first, 2 to the first, 3 to the second, 2 to the second. But actually, do you see the powers of x? The powers of x are uh, 3 times n in this case, because 6 equals to 3 times 2, 3 equals to 1 times 3, and 9 equals 3 times 3, which actually coincides with the factorial in the denominator. So that same um, 3n, okay, so let me first of all write the 3 to the n in the numerator, okay, 3 to the n in the numerator, and that times, okay, that's going to be a 1 times 4 times 7 times dot 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 times. Okay, in this case, I'm going to write a 3n. 3n, that's because, do you see how the 1 times 4, the 1, the 4, the 7, they differ by 3 units? Okay, and I believe subtracting 2 For n equals to 1, that's going to give us the 1 over here. In the denominator, what do we have? The 2 to the n, okay, the 2 to the n. And what else do we have? The n factorial we completed before, right? So that means, oh, and we're missing the powers of x to the 3n, all right? And, okay, that's the first series. I'm not going to have enough space for the second one. So plus c sub 1 times x plus sigma n equals 1 to infinity of -1 to the n. There will be also the same factor of 3 to the n in the numerator and the 2 to the n. Oh, wait a minute. I need to fix the factorial in the denominator, the previous one. That had to be 3n factorial, not n factorial. All right, what I was able to catch this. And then, well, so what do we have? The increasing product to 5 eighths. 2 times 5 times 8 dot 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 again. All these integers differ by 3 units, so 3n. And then, well, simply a -1 will take me back to a 2 for n equals to 1. All right? And that times in the denominator, well, that's an actually... Okay, let's have a look at the powers of x. So how do we get this 4? Do you guys agree? Do you agree that this is 3n plus 1? That is 3 times 1 equals to 3 plus 4 plus 1 equals 3 times 1 is 3 plus 1 equals to 4. And then how do we get the 7? 3 times 2 equals to 6 plus 1 equals to 7. What about the power x to the 10? The power x, which is 10 in this case. That is 3 times 3, which is 9 plus 1 equals to 10. So x to the 3n plus 1. And same over here. 3n plus 1 factorial. All right. So in this case, 2 series, and this is our final answer. All right. That's final answer for this exercise.